can't. But it is. It's paradoxical, and yet it works.
Hello, Year 11, or anyone who's taking AQA Physics P1 in about a week or so. So this is my walkthrough of Paper 1, things to look out for, things to sort of be careful of, and also predictions in terms of required practicals and equations to practice, and also some resources at the end which I'll put in the description later on. So let's get started. So first of all, this is question 1. Tides and wind are two renewable energy resources. So this is a question that looks like it's from chapter 3 if you're using the AQA textbook. You pretty much are, I think most schools do. So describe the difference between renewable energy resources and non-renewable. So they're asking for definitions essentially. So now, key stage 3, you'd have probably got away with saying renewables will not run out and non-renewables will run out eventually. You cannot say that. Okay, this question was so badly answered. I think only, according to the examiner's reports, only 20% of the people, the cohort, actually got 2 marks on this. So what you need to do when it comes to definitions or descriptions, look at the AQA exam spec. So words they tend to use. So renewable energy can be replenished. So this word comes up in the specification. Okay, you could use the word replaced. Okay, because again, that's in the specification, and therefore something like a non-renewable energy resource cannot be replenished or has a finite supply. Okay, or sometimes instead of the word finite, they might use the word limited. So just be careful. You're not allowed to say renewable energy resources will not run out and non-renewable will run out. Don't say that. Maybe key stage 3 you get away with it. Okay, for GCSE, stick to definitions in the specifications. So figure 1 shows a new design of a tidal turbine to generate electricity using the tides. So use the equation sheet to answer questions 1.2, 1.3. So write down the equation that links density equals mass. So it's density equals mass over volume. Write it in words, write it in symbols, they're both acceptable. Okay, so the mass of seawater passing the turbine each second, so that's your mass, and it's in the correct units, kilograms, so that's good. Density of seawater is this, so calculate the volume V. And it says each second, well, they've told you the mass each second, so you can work out the volume each second. So you don't have to do anything special with the formula. You just have to put the numbers in. So remember the sort of way they'd like you to do it. Rho equals m over v, then they'd like you to substitute first before you rearrange. So 1030 is equal to 824000 over v. Okay, so you'll get your first mark there, and then rearrange for v. So v is equal to 824000 over 1030. So if I put that in, I get a volume of 800 meters cubed. So density, I will come back to it later. The density is a required practical that's not been tested for a short while. So I recommend that you do go over that required practical. I'll go over a grid later on, just showing you how I've come to this this sort of prediction. Okay, and also in the description, I'm going to share some links to some past paper questions for you to practice anyway. Okay, but the formula itself is really reasonably easy. Just remember with density, especially if it's a required practical, what makes it a level 3 question? It's going to be the method. What could they ask you in the method? How do you work out the volume of an irregular object? Okay, that's always the most difficult thing. Okay, so this question was done quite well, so there's no issues here. So let's move on to the next question. Okay, so the speed of the tide or the speed of the wind past the turbine is called the flow speed. Okay, so that's just the amount of particles that pass it per second or per minute, it depends what it is. So figure 2 shows how the power outputs of a tidal turbine compares with a wind turbine for different flow speeds. So as flow speed increases, power output increases. Okay, so as you can see, as the x-axis increases, the y-axis is also increasing. give two other conclusions that can be made using information from figure 2. So basically, you got to use the data, you got to use the shape of the curves, and so on. So first of all, this question was terribly answered. I think only, according to the examiner's report, only 10% of the cohort got 2 marks. 1 mark, I think, is 30% of the cohort. So that is really bad. So people are not describing graphs as you see them. So first of all, let's look at what we can say. When it gets to from there to there, the pair is 0. So we can say that. So from 0 to 0.25 meters per second, the power equals 0 from both. Okay, so always start off by stating obvious things. The other, probably most obvious thing you can get from here, before you've even distinguished between one and the other, is always describe, is it linear or non-linear? Okay, so always start off with that. Well, clearly it's non-linear. So it's a non-linear relationship for both. Okay, so they're not proportional in any way. So you've got it. There's 2 marks, and people weren't picking these up. These I haven't even described the difference between a tidal turbine or a wind turbine here. No, all I've done is just looked at the data. What does the data tell me? However, let's have a look at if. Let me just do number 3. What sort of information could you pick up out of it? Well, if you look at the power from a wind turbine, it's always greater than the power from, the power from the tidal turbine, is always greater than the power from the wind turbine at any speed above 0.25. So if you take, say, 1, can you see that's the wind turbine there, and that's the tidal turbine. So just make sure if you are going to describe, you're going to compare both, just be very specific. So I can say at any speed above 0.25 meters per second, the tidal turbine produces more power. Okay, so those 3 hopefully are the most obvious things you could talk about. Okay, so again, it's not really knowledge you need to know. This is interpreting graphs. Okay, identifying patterns, describing features of the graph, and so on. And like I said, only 10% of the cohort got this correct, which is a bit worrying, but it is what it is. Just make sure you could do better. All right, so moving on to the next bit. So figure 3 shows the turbines used to obtain the data. So the wind turbine 100-meter diameter, and the wind tidal turbine is 10-meter diameter. So compare the environmental impacts of the wind turbine and the tidal turbine. So what you have to do here, environmental could be to do with the wildlife around it, or it could do with the cost. Okay, so so let's if you look at state the obvious things first. So we can see the wind turbine is bigger, and because it's bigger, it's using more materials, isn't it? If it's using more materials, it's going to cost more. So there's an impact already. If it's going to cost more, it needs more resources or more materials. So that's the first comparison. So you have to compare one with the other. The other thing you can say, wind turbine, what do we know about them? Well, they're for visual pollution and their noise pollution. Can't say that for a tidal turbine because you can't see it and you probably can't hear it underwater. Okay, so and the other thing, wind turbine, depends to what extreme. You could say they're harmful to birds. Birds could get sliced up inside that. Okay, so I've named quite a few environmental impacts. Well, because it says compare, you've got to say something about the tidal as well. So tidal turbines, yes, they're smaller. Okay, so probably cheaper, but they might be more expensive to install because they're underwater, and they're probably harmful to fish, maybe. Okay, so you got to tell me something about both. So let's talk about wind turbines. are larger. Okay, so cost more, right, and cause more visual and sound pollution. So again, most of these are linked to what I'm seeing. I don't know anything intimate about turbines to be able to say anything else, but hopefully you can see I made an observation, then I made conclusions or deductions. And then tidal turbines. First of all, I mean, you could say they produce more power, but we know that anyway, are smaller and are harmful to fish. Okay, so you could have some sliced sushi on the way. Right. Okay. So again, like I said, this question for some reason, this one itself, people did reasonably well, so there's no cause for concern from the examiner's report. But obviously, marks beforehand. Don't forget, each mark is like 1%. You lose a few marks, there's 3%. If you add that up over each question, 10%, you're losing 15%. When you shouldn't do, that's probably one, maybe two grade boundaries, which is a bit of a disaster, isn't it? Okay, so let's move on to question 2. Right, so this is a required practical. All right, so this required practical has been done quite a few times now, and I successfully predicted it last year that it was going to come up on the 2025 paper. So don't expect it to come up again. Okay, but doesn't mean you don't practice it. Of course, practice it. Okay, so give one hazard in the investigation. So if you look at it, you've got a joule meter to measure the energy, power supply to supply the energy to the heater to warm the water, and then you've got a balance to measure the mass of some things. So what's one hazard? Well, the only thing that really sticks out, what sort of thing could someone potentially do, is you could spill the hot water. Okay, that's the most obvious thing. Um, you could say broken glass. Okay, so and the other one is that you've got a hot heater. Okay, so it's only asking for a hazard. Obviously, I've given you a few here. That's just to improve your knowledge of it. What they could ask you, which they haven't here, they normally would ask this, is what's the precaution? Well, to avoid spilling the hot water, what would you do? You would hopefully realize, put the beaker at the center of the table. Sorry, sorry. Okay, and things like when it comes to the hot heater, don't let it, first of all, let it cool or don't touch it at the heater, lift it up from the connections. Okay, but they're not asking for precautions, but they could do, and they probably should have actually. All right, so describe how the student could determine the specific heat capacity of water using the apparatus in figure 4. Now, in school, most likely you would have done the specific heat capacity of a metal block. So 6 marker, 1 mark is always the formula. So I'll write it here on the side. E equals mc delta theta. So that's the underlying theory. And you have to determine C. So rearrange the formula for C. C is E over m delta theta. Okay, so if you look at it, what is it you've got to measure? You've got to measure delta theta, which is a change in temperature, which is what the thermometer is for. You've got to measure the energy. Now, they are being kind to you here because they're using a joule meter. Okay, in school, you would use the voltmeter, ammeter, um, and you'd use the stopwatch. Okay, so I'll just tell you what you would have done. You would have done energy equals power times time over m delta theta, and power, because it's electrical power, it's power equals IV, so you'd have done IVT over m delta theta. They haven't here. They've been kind of giving you joule meter. Some schools do have joule meters, but you certainly don't have enough for like 5 or 6 groups. They may do. I think we do in our school. So now you got to, for every quantity in this E equals E over m delta theta, you got to explain to me how you're going to do each one. So first of all, the big issue here is you've got to measure the mass of the water. Okay, so in order to measure the mass of the water, or you have a look at the picture, you can't measure that directly. Okay, you can't just pour the water onto the balance. So we've got to come up with a procedure here. So I'm going to write the procedure here on the side. Obviously, this paper will be a bit larger, and you've got some extra space on the next page, but I'm not going to look at that yet. So what do you need to do? You need to record mass of empty beaker. Okay, what would you use? You'd use the balance. All right, once you recorded the mass of the empty beaker, then you would fill the beaker and record the mass. I'll call it the new mass. Then what would you do? Well, how do you work out the mass of the water now? It's the mass of the new mass minus the mass of the empty beaker. So this is a calculation. So calculate mass of water and explain how. So make sure you very explicit about what you're recording and what you're calculating or processing. Calculate the mass of the water is, so it would be new mass minus empty beaker. Okay, so don't forget, when it comes to procedures, it's got to be logical, sequential, such that if you gave it to somebody else, complete stranger, they should be able to follow it and do it accurately. Okay, so now you got the mass, your water in the beaker, record temperature of water. So you record the temperature before you heat it up. Okay, switch on power supply and joule meter. Okay, and then after a fixed amount of time, switch off after fixed amount of time. That time is up to you. The greater the time, the more noticeable the change in the temperature, which is more useful to you. Switch off after a fixed amount of time. Okay, and then all you got to do, measure the final temperature. So you're going to measure the change in temperature. Measure final temperature. Let's not draw over my head. Okay, so calculate the change in temperature, so delta theta. And then you should be able to just record E from the joule meter directly. If you do not include the formula, then you lose a mark. Okay, so you must include the formula. Usually in this part of the method, they ask you about safety and so on, but they've asked you that in 2.1, so that's fine. Now, that is your thorough 6 marker. There's 6 markers all over the place, so make sure, whatever 6 marker you copy, memorize, whichever YouTube video, whatever, make sure you copy it logically and sequentially. But this has come up now. I don't expect this to come up again. So let's move on to what they could potentially ask next time. Now, there's a bit of extra space. I'm just going to show you what you would potentially have found. If you did temperature against time, you would get a graph that looks like, looks like this. Okay, so initially for this bit here, there's no change in temperature. The question is, well, you've already switched it on, so what's happening? Or you're supplying energy. Maybe the heater's still warming up. Okay, so one of the things you should have done is preheat the heater before you put it in. Okay, therefore you wouldn't have this bit here. Now, a lot of people ask, well, you've got this, how do you work out the specific heat capacity from this? Well, you've got temperature and time. So if you look at your formula, E equals mc delta theta. And E, well, it's no good to us in this way because, well, we've got delta theta, we've got T, but we haven't got time. But we have got time because E is equal to PT. PT equals mc delta theta. Now, you can actually work out the gradients of the linear bit. That's, if you think about it, is delta theta, change in temperature over time. So that means, can you get the formula in terms of that? Yeah, you can do. So you can take T to the right hand side and MC to the left hand side. So P over MC is equal to delta theta over t. So your gradient of the linear part, so if you do have to do it, pick 2 points at least half the length of the linear part of the line. Work out the gradient. That gradient is now equal to P over MC. Okay, so therefore, grade C is equal to P over mass times the gradient. If you had to. Now, this is not, like I said, they've sort of done this practical to death, but it always comes up as a theory question anyway. So they could actually ask you to do this in order to do some calculations. Okay, so then usually the value for C that you get is always too large compared to the actual value. So clearly something has gone wrong. So one source of error in the experiment was energy loss to the surroundings. Suggest one change. So what would you do? Most obvious one. Suggest one change to reduce the energy loss. You would insulate the beaker. Okay, and that's just to reduce the energy emitted by radiation. The other thing you could do is add a lid on top of the beaker. Obviously, you're going to slot the thermometer and the heater in, and that will reduce the convection energy transfer. Okay, so, and this is not new to you, this is stuff you've seen before. So students value the specific capacity is 4,410. So as I said, you'd always get a value bigger than. Okay, the actual value for the specific capacity is 4,200. Calculate the percentage difference. So first of all, work out the difference. So the difference is really straightforward. Just subtract the big number minus small number. So 4,200. So that will give you 210. And then it says give it as a percentage. So basically, what is 210 as a percentage of the actual value? So you just do the percentage difference because you've just calculated the difference is 210 over 4,200. Numbers seem to disappear. So, and then you've got to times that by 100 to get it as a percentage. So I got 5%. Okay, so this question, like I said, this required practical 10 marks. I don't expect it to come up again. Okay, so I'm not saying don't practice the require practical, but I would probably emphasize others at this point in time. Okay, let's move on to the next question. So, a student investigated how the current in an LED varies with the potential difference across the LED. Okay, so LED light emitting diode. What does a light emitting diode do? It only allows current to flow in one direction. So if you look in this particular diagram, current, how does current flow in a circuit? Conventional current, positive to negative, so it's going this way. Will it work? Yes, because it only works when it's this way. Here, the resistance is 0, or we'll come to that in a second. But if, let's say, for example, you connected it the other way, and you try to put a current through it, what's going to happen? It's not going to work. So here we say the resistance is infinite. Okay, but let's have a look at the question anyway. All right, so figure 6 shows the results. So you got the current. So this is your standard IV graph for a diode. Obviously, they've only done the positive scales. Now, give one way the student could have varied the potential difference across the LED. So there's two ways you could have done it. What you would have done in school most likely, you'd have just flicked the power supply voltages from 2 to 4 to 6 to 8. Okay, so you could have just said that. So change the PD of the power supply. PD is just another word for voltage of the power supply. The other thing you could have done, you could have kept the PD fixed, the voltage fixed on the power supply at maximum value, and then use the variable resistor to alter the currents and therefore altering the PDs in the circuit. So variable resistor varies the resistance. If you vary the resistance, it has a knock-on effect on the currents also. So it's just something to remember. So that's nice questions. They're giving us a graph. Most likely we're going to end up having to use it in a second. Okay, so use the physics equation sheet to answer the question. So which of the following connects I, V, and R? So V equals IR, your go-to formula for anything electrical circuits. All right, so determine the resistance of the LED when the PD across the LED was 3 volts. Okay, now just another thing I should have said. This IV graph you've seen before, when it's in the negative, it stays 0, and then it suddenly increases there, doesn't it? So when you connect it the wrong way, you have infinite resistance, so you have zero current. But let's have a look at this question. Determine the resistance when the PD across the LED was 3 volts. So let's use the figure 6. Obviously, we've got to find 3 volts there. So there's 3 volts. I'll go up. It's here. Okay, so if I go across, I can't read that very well, but I'm sure it's in the middle. So that's 0.125. Obviously, you're going to be a bit more accurate than me. Use a ruler, of course. Okay, so what do I know? When V is 3 volts, I is 0.125 amps. Okay, so what formula connects those? Because they're asking me to work out resistance. So R is V over I. So just put your numbers in, that wasn't too difficult. So 3 over 0.125. So if you put that in, I get 24 ohms. Okay, so 24. So that's nice and easy. If there is a graph somewhere, usually you have to use it. Obviously, we saw one for the wind turbine. We had to interpret it. Here, we're going to have to pick some values from it. Okay, because they asked about the IV graph for the diode. My impression is if they're going to ask about an IV graph, again, it'll most likely be the filament bulb. Reason why they ask about the filament bulb a lot is because you can apply particle theory to it. Okay, and I'll go over that in a second. So the student reversed the connections to the power supply and varied the potential difference across the LED. Explain why the ammeter displayed a value of 0.0 amps for all the values of the potential difference. So what did I just say? So if you remember, when it goes this way, it works because the resistance is 0. And when you have if you go in the opposite direction to the diode or the triangle, that doesn't work. So that's resistance is infinite. And I think that's the answer they're looking for. Resistance is infinite in the opposite direction. Okay, therefore the current is 0. So don't forget, whenever you talk about resistance, you have to talk about current as well. Well, they've actually talked about current for us. They said the current is 0. Resistance and current are inversely proportional, aren't they? Because R equals V over I. So if you ever talk about current, talk about resistance. Current is 0, resistance is infinite. Current is increasing, resistance is decreasing, and so on and so on. Now, what they haven't asked about for a short while is the IV graph for a bulb. Okay, and it looks like this, doesn't it? Now, why is it? What's happening here? We'll just look at the positive part. As V increases, I increases. So that's the linear bit there. Okay, so now this here is what it'd be if it was a fixed resistor. Okay, so this is clearly not following the path of a fixed resistor, so the resistance is changing, and obviously that goes in the negative also. But so let's try and explain what's going on here then. So as V increases further, what happens to the bulb? Obviously, it's getting brighter, but as it's getting brighter, it's getting hotter. Okay, so if the bulb gets hotter, that means the atoms in the wire of the filament in the bulb, they're vibrating with greater amplitude. So lattice atoms vibrate with larger amplitudes. Because what is it that's flowing through the wire in order to have a current is the electrons. So what does that mean? There's increased collisions between electrons and atoms. Okay, so the electrons lose more energy, so they move slower. So that means less current and less current. So can you see why the graph levels off? Less current, more resistance. And more importantly, what's the take from here? Increasing temperature means larger resistance. That's why it's important to control the temperature in a circuit. That's why you got these big fans in your laptop to cool your circuits down. So so increasing temperature, larger current. So how does a normal circuit, if you remember this one, how does a normal circuit do it? They have a variable resistor because that will help them control the current. Okay, so just be mindful of that. So they could potentially ask you that. Okay, let's move on to the next question. Right, so manufacturing a car produces carbon dioxide. Sounds like another chapter 3 question about resources and pollution and so on. So explain one environmental problem caused by the emission of carbon dioxide. So try to link it to an effect that you see happening around the world that's somehow linked to carbon dioxide. So what do we know? Carbon dioxide is it's a greenhouse gas, isn't it? Okay. Because it's a greenhouse gas, it causes greenhouse gas causes global warming. Okay, so make sure you try to link it to a change in our climate in some way. Don't just say climate. You could say climate change, but it's best to be specific. For example, you could say things like sea levels rising, extreme weather conditions, desertification, etc., etc. Okay, right. So let's move on to the next bit. So we've got this graph again. So clearly we're going to have to do some extracting data maybe or describing patterns. Both linear, of course, this time. Figure 7 shows the carbon dioxide produced during the lifetime of two types of cars. So from the moment they walk out, so 0 is the moment they go out to the showroom. That's when they buy it. Up to 100,000 kilometers. So, okay. So what mass of carbon dioxide is produced during the manufacture of the electric car? So what that means is how much carbon dioxide was emitted before it even left the showroom, okay? Because that's how much it took to build it, all right? So if you think about it, that's actually the start point, isn't it? Okay, so that here would be for the electric car, which is a dashed line, it's that. So that's about 8,000 yeah, so that's 8,000 kilograms. Right, okay, so at one distance, the immense carbon dioxide emitted by both cars is saying, what is this distance? So that's where they intersect. So that's that point there. So if you go down, so let me just see if I can read that clearly. I think I made a mess of that 9, but it's about 17,000. But just check the mark scheme for that. But hopefully you can see how I do it. It's where they're both equal. Okay, so that's nice and straightforward. So take those. Now, some energy resources emit carbon dioxide when used to generate electricity. The battery-powered car does not emit carbon dioxide as it's driven. Explain why more carbon dioxide is produced as the distance traveled by the electric car increases. So even though the car's not burning fossil fuels to emit energy, emits carbon dioxide, sorry, what is it doing? You still have to charge the thing. Okay, so to charge it, you need to plug it into an electrical socket of some sort. Well, to produce electricity at the household or at these electrical charging stations, you need to be burning fossil fuels, gas, coal, and oil. Okay, now this question, believe it or not, only 15% of the cohort got maximum marks. In fact, only 35% of the cohort got 1 mark. People are sort of linking it to the person sitting in the car. I don't know what the person's doing to be giving those amounts of carbon dioxide, but still. So the real answer is, well, even though electric cars don't produce any CO2, you still have to charge them, so you still need electricity, so you still need power stations to produce electricity, so you're still burning fossil fuels. So batteries in electric cars need charging. Okay, so fossil fuels needed to make the electricity. Okay, so which two of the following energy resources do not emit carbon dioxide when used to generate electricity. So what that essentially means is do not emit. It just means what do you not burn? Okay, so biofuel, you're basically burning living organisms, think of plants, trees, leaves, etc. But obviously we can replenish the trees, so that's why it's classed as renewable. Nuclear, we're not burning anything. Okay, that's chapter 7 on the textbook for you. Oil, clearly we burn the oil, combustion engines and so on. Solar is you're not burning anything. Okay, you're just using light energy directly to produce electricity if it's a photovoltaic cell, or if it's a solar panel with water pipes in it, you're heating the water directly, and then they're using that for washing and so on. And then wood, clearly you're burning it because the only way to get the energy out of it is through burning, isn't it? So nuclear, which one are they talking about, is fission. Now I'm going to come back to this because they have not talked about fission reactors in um, uh, this paper at all. So I'm guessing they're going to talk about nuclear fission, the fission reaction, nuclear reactors in a bit more detail. So coincidentally, that brings us on to the next question. So describe what is meant by isotopes of an element. So definition of an isotope, same number of protons, because it's the proton number that defines what element you are. Same number of protons, but different number of neutrons. You don't need to say any more, that is your definition. But obviously, consequently, if you've got the same number of protons and you've got more neutrons, or less neutrons, let's say, then you're going to have a different mass number. Okay, but that's not part of the definition. That's just another observation for you. All right, so explain how nuclear fusion releases energy. So they're asking about nuclear fusion on this one. Okay, so will they ask about nuclear fusion again? They could do, but most likely they'll probably ask about nuclear fission in detail. In fact, most likely nuclear fission a chain reaction and so on. But maybe they'll ask both. Okay, so what is nuclear fusion? How nuclear fusion? Now, what nuclear fusion do we know happens in stars, or in our star in particular? So H2 plus H3 isotopes of hydrogen fuse together, join together, and they produce He42. Can you see some of the mass is missing because the top numbers don't balance up? So what's happened to the missing mass? That gets converted to energy. Okay, so try to remember that if you can. It's quite an easy equation to remember, but let's put it into words. So what happens? Two light nuclei fuse, or they like to use the word join. Do not use the word collide. They don't like that. To form a heavier nuclei. So clearly helium is more heavier than those. And then that's the first mark, and then some of the mass, so can you see the top numbers? 2 and 3 is 5 on the left hand side, is only 4 on the right. Some of the mass is converted to energy. Okay, again, this question, only 20% of the cohort managed to get 3 marks here. Okay, 2 marks, 30% of the cohort, and 1 mark, 15% of the cohort got 1 mark. So it was really badly answered. All right, so go back to your definitions for these processes. Go back to nuclear fission. Make sure you can describe it. Daughter nuclei, U235 absorbs a neutron, becomes U236, becomes unstable, splits into 2 daughter nuclei. 3 other neutrons are released, plus lots of energy released because of the missing mass. Some of the mass converted, but these other neutrons then go on to find other U235, cause more fission of other U235s, and then talk about how do we control it in the nuclear reactor. We use control rods to control the rate of reaction by lowering them or raising them. What's the job of the control rods? Is to absorb the neutrons. How do we slow the neutrons down to ensure that they collide sufficiently collide or get absorbed into U-235, you use a moderator like heavy water to slow it down, and we call them thermal neutrons. Okay, it's all there. It's all very factual. There's nothing to think about really. Okay, so but with fusion energy, fusion releases more energy than fission per unit kilogram. Okay, so that's, and it's clearly not as dangerous. It's just hydrogen 2, hydrogen 3. The deuterium, tritium is found in heavy water. Okay, but there's a lot of huge amounts of energy given off. So let's move on. So fusion reaction releases large amounts of energy. The fusion reaction takes place in a reactor. Explain why the walls of the reactor should be made from material with a very high specific capacity. So specific capacity is going back to chapter 2 now, isn't it? What do you know about specific capacity? Large specific capacity. Let's put this down. So large C and small c. Okay, it's large C means takes longer to warm up, takes longer to heat up. This heats up quickly. This takes longer to cool because it's obviously absorbed more energy. This cools down quickly. And larger C means needs more energy to raise 1 kilogram by 1 degree Celsius or 1 degree Kelvin, if you've heard of that, but don't worry if you haven't. So that's essentially it. So what does that mean? So why the walls of the reactor? And then obviously, you could write the opposite definition for a small specific heat capacity. Will only a small amount of energy is needed to raise the temperature of 1 kilogram by 1 degree Celsius. So what does it mean then? If you've got very high specific capacity, that means you'll have a smaller temperature rise for large amounts of energy, because that's what they're talking about at the start of the question. Okay, so therefore, what is the consequence of that? Less chance of a nuclear meltdown or an explosion, less chance of melting. Okay, so usually the reactors, the cores are made of steel. But again, that's just extra information if you're ever interested in what goes on in a reactor. So nuclear fusion is safer than nuclear fission. Nuclear fission can lead to an uncontrolled chain reaction. So get ready for that, I think. Give one consequence of an uncontrolled chain reaction. So what would happen? The core will melt down. So we say nuclear meltdown. That would mean that will knock-on effect of that is there'll be a big explosion. So the reactors will explode. Okay, so that's nothing new. I mean, it's sort of everyone knows about these sort of things. You see it in the news, you may have seen it in the movies, and so on. So yeah, so expect a nuclear fission question. Okay, let's move on to the next question. So figure 8 shows a battery-powered hand warmer that contains a heating pad. Battery transfers energy to increase the temperature of the heating pad. Heating pad has a mass of, and that's in kilograms, so that's good. When the hand warmer was switched on, the energy transferred to the heating pad was 800 joules, so that's your energy. Specific capacity is this. Calculate the temperature increase, so they want delta theta. Okay, so get in the habit of labeling what you've got, make sure they're in the correct units. What connects all of these? Hopefully you realize it's the specific heat capacity formula, E equals mc delta theta. Where's the first mark? Is putting the numbers in, isn't it? So 800 is equal to 0.2 times 1600 times delta theta. So then if you want to neaten it up, you can do, or if you're going to rearranging, that's up to you. Not really stopping you. 320 times delta theta. I'm just going through every step so you can see the process. Now I'm going to take 320 over. So delta theta is 800 over 320. So if I put that in the calculator, I get 25 degrees Celsius. Right, so that's nice and easy. So let's move on. Okay, so the hand warmer was powered by a 5-volt battery. The battery transferred this much energy, and this is not in the correct units. So that's 180 kilojoules. That's 180 kilos a thousand, 180,000 joules. Calculate the charge Q. Right, now Q. two formulas for Q that you'll see in the formula sheet. E equals QV and Q equals IT. Well, there's no I and there's no T here, so I'm clearly not going to use that one. I'm going to use E equals QV. So even though you have no idea how this works or whatever, you can see numbers, you can see what they represent, what symbol, therefore punch it into the formula, and 4 marks for this. 1 mark is obviously clearly for the conversion. Okay, so if you forget to convert and you get an incorrect answer, you lose 1 mark only. So Q times 5, so Q is 180,000 over 5. So if I put that in, 36,000 coulombs. Okay, so should be okay with that. That's 4 easy marks. Just be prepared, lots of unit conversions, lots of rearranging, because obviously they give you the formula sheet now. So don't get in the habit of doing questions where they're asking for the subject of the formula. So don't do one where they're asking for E. Okay, it's not useful. Now, where have you seen these two formulas together? If I put this with this, so E is QV or Q equals ITV. So remember, this is the formula for electrical energy, or E equals IVT. And what's IV? That's P, isn't it? So can you see there's links with all these formulas? So just be prepared to use them, interchange them, and so on. Okay, so let's move on. Right, so this is where it gets a bit sort of interesting. So the circuit inside the hand warmer can be connected to a mobile phone to recharge the mobile phone. So essentially what you've got a circuit with 2 resistors in parallel. Okay, I've missed out the switches because I'm not interested at the moment. Now, what do you know about parallel circuits? Okay, these are the facts you need to know. V is the same. So if that's 5 volts, that's 5 volts, and that's 5 volts. Okay, I, now how do you work out I? Well, there's the current I, and when this is I still. And when it gets to the junction, it splits into I1 and I2. So I is equal to I1 plus I2. And the other thing you need to know, so obviously the current splits, let's just write that down, is the really important thing. The more resistors in parallel, the smaller the total resistance. Okay, just for reference, let me just do series for you. So series, again, now if you had 2 identical resistors, what would you know here? V is shared. So for example, if that was 10 volts, that could potentially be 5 volts, 5 volts if they're identical. I is the same throughout, so the same current travels all the way through the circuit. That doesn't change. Okay, but the total resistance is R1. Sorry, this is R1. That's R2. R1 plus R2. You've got to be able to use that one. Okay, there is a formula for parallel resistors, but it's not on the spec, so they're not expecting you to put any numbers in. But the more resistors in series, the greater the total resistance. If the total resistance drops, the current increases. Okay, if you look for series, if the total resistance increases, the current decreases. So let's have a look at the question then. So explain how closing both switches S1, S2 affects the power output of the battery compared with only closing switch S1. So power, they're asking about power. Now, what do you know about power? Power equals IV. Okay, that's your go-to for power. Just like resistance, it's always V over I. This is your go-to for power. So what do we know? If you close S1 and S2, you've now got 2 resistors instead of 1 when you only closed S1. Okay, so that means total resistance decreases. If the total resistance decreases, total current increases. And if total current increases, because the voltage is the same, power increases. And you've got to sort of explain, so you've got to quantify, or how have you come to that conclusion? Because power equals IV. These stay the same, but current has increased. 80% of the cohort got 0. Okay, so as soon as you see parallel circuit, blurt it out, all this theory if you want. If you see series, just blurt this out, and don't forget what's the knock-on effect on the current. And then just coincidentally, current is part of power, so that's how I got to that. Okay, so let's move on to the next question. So some atoms emit radiation. Why do scientists sometimes change the model used to describe the structure of the atom? So this is Rutherford scattering. The plumb body model then to Rutherford scattering. So what happened? New evidence is discovered. So there was the alpha scattering experiments, wasn't it, which couldn't be explained using the plumb body model. Okay, so describe the difference in irradiation and contamination. Again, don't make up your own. Look on the specification. The definitions are there. You've got to blurt them out, as is the definitions on the specification, irrespective of what you've seen anywhere else. And to be honest, I've seen a few definitions on the website. They are pretty much identical. Even if you put in ChatGPT, it gives you a pretty identical uh, description compared to the spec. So this is exposure to radiation. So think of it as someone sprayed something in the room and you're now exposed to that smell. Exposure to radiation without contact. Okay, so you're not trying to touch it. But the key thing is you do not become radioactive yourself. Okay, so this is above and beyond. I'll put this in brackets. That's just your understanding. Now, what does contamination mean? Basically, you've physically touched it now, haven't you? So it's now transferred to you or got inside you. So therefore, you do become radioactive. So the material, radioactive material, is transferred onto the person. And if this happens, yes, you will become radioactive. So we're going to put this in brackets. It's not often this comes up as a definition, so I don't expect it to come up again. So let's move on to the next one. Right, so you'll always get an alpha, beta, gamma decay. So you'll always get one of those. So this one, this is clearly alpha decay because alpha is helium-42. Do the top line. Top line is conservation of mass. Bottom line is conservation of charge. So 210, so clearly you should be able to, well, if you need to use a calculator, go for it. No one's judging you, no one's looking at you. So 216, and then this one is 84. Okay, so 2 marks there. Make sure you grab those. So polonium 210 has a half-life of 138 days. So that's the half-life. So every 138 days, it's going to halve. So a sample of polonium contains 256,000 atoms. Calculate the time taken for it to reach 16,000. So they've given you the start point. So they're basically asking how many half-lives does it take to get to 16,000? So we can do that. So after one half-life, it would be 1 to 8,000. So that's 138 days. After two half-lives, after two half-lives, it's 64,000. After three half-lives, it's 32,000. And then after another half-life, it's 16,000. So how many half-lives is there? So look at the number of arrows. 1, 2, 3, 4. So 4 half-lives. Calculate the time taken. So it's basically 4 times 138 days. Okay, 552. You will always get a half-life calculation. If they're kind, it'll be work it from the graph, but that's probably a foundation question. It'll be of this effect. So make sure you keep practicing as many different ways of doing half-life calculations. Okay, so let's move on. A sample of polonium contains equal number of 209 and 210. 209, half-life 125 years. Polonium 210, half-life 138 days. So clearly, for it to drop to half its value, it's emitted, 210 is emitting a lot of alpha, beta, gamma per second. It must have a higher activity. Okay, so let's put that into context. So 210 has a shorter half-life, or we could say it the other way, has a shorter half-life. Okay, so what do you know about its activity? So 210 has a larger activity. So it's decaying, it's giving off more decays per second, larger activity. Okay, or essentially it takes less time to get to the half the original value. Again, after that, few half-lives it becomes safer. Right, okay, so again, there's not much in this question. They haven't really asked about dangers or ionizing properties, penetrating properties, uses in industry, whether it's smoke alarms for alpha, thickness control for beta, and also gamma for detecting leaks in pipes and so on and so on. So just go through the uses. They haven't gone through any of those examples yet. Okay, so let's move on to the next question. So scientists poured some liquid into a nitrogen into a container. Container was unsealed, so on and so on. Liquid nitrogen was at its boiling point when 9,950 joules, so there's your energy, transferred to the liquid nitrogen, 50 grams turned into a gas. So this is your mass, but it's not in the correct unit, 0.0. So divide by 1,000, 0.050 kilograms. So that's why you get 4 marks for this. You've already got 1 mark by converting. Calculate the specific latent heat, so L. So what formula connects E, M, L? So E equals M, L. So again, write down your numbers first. So 9950 is equal to 0.050 times L. So I've got 2 marks already. Then I'm just going to rearrange. L is 9950 over 0.050. And then let's just work out the answer. 199,000 joules per kilogram. Okay, so that's good. So should be able to do that. What they have not done yet, and I've seen a few times, they haven't combined these formulas together. Now you're thinking what formulas? E equals ml and E equals mc delta theta. So what I've sort of compiled some questions where in one question they have SL, specific heat capacity and specific latent heat together, whether it's combined in one 5 marker or whether it's 2 different parts of the same question. They will always do that. They always do this. There'll always be ML and there'll always be MC delta theta. So just look out for those. Again, I'll make a pack. I'll put it in the description so you can practice as much as you want or not. It's up to you. Okay, so explain how the internal energy of nitrogen changed as nitrogen turned from a liquid to a gas. So this is your classic, this graph here. Okay, so this is temperature, this is time. Okay, so this is melting, the first change of state, and this is boiling. Okay, melting is latent heat of fusion, boiling is latent heat of vaporization. What do we know? Latent heat of fusion is always it's not greater, it's the other way around. Latent heat of fusion is less than latent heat of vaporization. Latent heat of fusion is roughly about 300,000. Latent heat of vaporization is about 3 million. Why do you need more energy to change a state of something from liquid to gas? Because when you go from solid to liquid, you're only breaking a few bonds. When you go from liquid to gas, you have to break every bond. So clearly you need a lot more energy. Okay. Notice that there's no change in the kinetic energy at this point because there's no change in temperatures, is there? Okay. These are MC delta theta. Okay, they're because of a change in temperature. Okay, so now what they're asking here is really about the energy. So what do we know? Internal energy is equal to the internal molecular kinetic energy plus molecular potential energy. This is how fast they're moving, basically a reference to the temperature. This is how far apart they are. So this is a reference to the state of matter. So something like a gas has a higher potential energy because the particles are further apart compared to liquids, compared to solids. So the internal energy of a gas particle is greater than the internal energy of a liquid or a solid because they're moving faster, so larger kinetic energy, and they're further apart, so larger potential energy. So let's have a look at the question there then. So this what I've drawn, you got to recall straight away when you see the word internal energy and so on. So explain how the internal energy of the change as the nitrogen turns from liquid to gas. So first of all, internal energy increases. Okay, so that's just my statement. Why? Due to increase in potential energy or molecular potential energy. Okay, and then why is that? Because particles move further apart. This question, out of the whole cohort, only 3% got 3 marks. Only 1% got 1 mark. Sorry, only 10% got 1 mark. So this was poorly answered. And there's no change in KE because the temperature is constant during a change of state. Okay, so you've really got to be hot on your definitions and descriptions and observations. Okay, so let's move on to the next bit. After nitrogen had boiled, the temperature of the gas increased. Okay, explain how pressure in the container changed as the temperature increases. So if temperature, start with the obvious, so build up your answer. Temperature goes up, particles move faster, or kinetic energy of the particles increases. So that's the obvious stuff. Now, what's going to happen? These particles in a container, if they're moving faster, think of people in a room moving faster. Let's say you blindfolded them. There's more chance of a collision, or we say the frequency, not necessarily more collisions, or how many collisions per second. So you got to be specific. Frequency of collisions increases. Okay, therefore, not only is there more collisions per second, they hit the walls with a larger force. It's like you running into a wall more often and harder each time. So they hit the wall with larger force, and therefore the cumulative effect of that, the resultant force, is larger from all particles, and therefore pressure increases because what is the definition or formula for pressure? Pressure is force over area. Okay, so for the same area, force is greater, so pressure increases. So what they have not asked about yet is PV equals a constant. So you may remember this. Practice this formula. It hasn't come up for a while. This was Boyle's law, wasn't it? This was basically stated that pressure is inversely proportional to volume, or pressure against 1 over volume is proportional. So make sure you can use that formula. Be careful. I think it's going to come up. Okay, so, and again, I've made some questions. There's not many on AQA. In fact, there's not many on many GCSE exam boards on this. So I've really had to dig deep to find some. So just practice them. Again, it's in the description. I'll put some exam packs for you to have a go at. Okay, and mark schemes are on there. Right, let's move on. Let's just jog on as quick as we can. Okay, so top of the container shows a garden water feature. Water has an electric motor that pumps water from the bottom to the top. Pump transfers this much GPE and it's in joules, that's fine. G, determine the mass of water passing through. So you've got your H here, which is in the wrong unit, so it's 0.7 meters. So there's my first mark out of the 4. So then let's write our formula down. EP is mgh. Put your numbers in. 0.343 is equal, we've got to work out the mass, sorry. M times 9.8 times 0.7. So we can I'll need to up, no, I won't need to up, I'll just rearrange. So M is 0.343 over 9.8 times 0.7. You can neaten the right hand side up of the previous line first if you want, it's up to you. Just be careful, is 0.05 kilograms. Okay, so that's a nice starter question. Can't complain with that. Right, let's move on then. Anything you need to know about that? Not really. You'll always get an MGH half mv squared half ke squared, or half ke squared, but without the f equals kx, which is Hooke's law, which is paper 2. Okay, but on paper 2, you'll get f equals kx and half ke squared, because paper 2, the assumption is it's a bit synoptic, so you need to remember stuff from paper 1. Right, the power of the pump is this, and the resistance is this. Right, straight away, what formula connects these? Whether I'm going to use it or not is another thing. Power equals I squared R. So I'm just going to put question mark, as in, are we going to use this or not? No, because it's 6 marks, you will have to combine formulas. Okay, and not only that, you're going to have to convert some units. So calculate the charge, okay, question mark, in this time t. So here's your conversion of units. We don't like minutes, we like seconds, so it's 30 times 60, which is 1800. So I've got a mark already. Okay, so I've got to work out charge, and what formula connects these two is Q equals IT. So we've used both Q formulas, so expect that. All right, so in order to work out I, I've got to use P equals I squared R. So let's do that then. So P equals I squared R. So let's put the numbers in to get the first mark. 86 is equal to I squared times 6. So I squared is equal to 4.86 over 6. So, and then square root that. Okay, that gives me 0.9. Then we're going to put this into Q equals IT. So Q is equal to 0.9 times 1800. Okay, so this will give you 1620 coulombs. Okay, so again, look at quantities. Make sure you can identify the quantities and then link it to formulas. And that's all I've done. I have no idea what the question. I've actually read the question, but I haven't actually read it ready. I'm not interested. I can see numbers. I'm going to punch them in. Okay, so the pump motor breaks and is replaced with a new motor. The new motor has the same power output but greater efficiency. So efficiency is useful output over total input. Now this could be useful output, useful power output over total power input, or it could be useful energy output over total energy input. But in this case, we're using the power one. Now, explain how the new pump would affect the flow of water in the feature. So what they're asking about is the output. Well, if you've got a greater efficiency, that means the amount of energy wasted is less. So less energy wasted. So if you waste less energy for the same input, so that means a greater useful output. And if there's a greater useful output, what would happen to the, what are they asking about? Flow rate, affect the flow of water. So the flow rate increases. Okay, so this question was done reasonably well actually. So expect these 6 markers where rearranging, combining formulas and converting units. So just keep an eye out for that. All right, talking about that, figure 12 shows a device that accelerates a toy car at the start of a racetrack. Okay, pulling the handle compresses the spring in the device by this. So this is your extension. It's in meters. That's good. When the handle is released, the energy stored in the compressed spring is transferred to the toy car. They give you the spring constant. The only formula you know with spring constant on paper 1 is E equals a half k E squared. And they give you the M, and we could use that anywhere. But calculate the maximum possible speed. So where have you seen speed on paper 1? That's kinetic energy. This is elastic energy, by the way. And this is kinetic energy, which is a half E squared. So again, it's another case of converting, energy to convert, doesn't look like there is. It's a conservation of energy question, isn't it? So conservation of energy. So the energy before, so the E elastic before is equal to the kinetic energy after. Okay, so the half k E squared equals a half v squared. I can just cancel the half straight away. We don't need to worry about them. So let's put the numbers in. So we got k, which is 64 times 0.075 squared equals, and then m, we've got 0.052 times v squared. Okay, so I can rearrange for v squared. So v squared is 64 times 0.075 squared over 0.052. So once you work out, then you can square root it, and that'll give you v. So I've got on my calculator was 2.631. It wanted two significant figures, so that's where the next mark is. So even if you get the wrong answer, give your wrong answer to two significant figures, you still get a mark for that. So my answer is 2.6 if it lets me right. Okay, now conversion of energy is very popular. What they haven't done is GPE to KE, whether you drop something or whether you throw something up in the air. Because of that, and I don't think I've seen it on a couple of past paper, couple of years now, I think it's going to come up. So what I've done, again, I've made an exam pack with GPE to KE questions, or GPE conservation of energy questions, let's just say, because they could be elastic again. So make sure you have a go at those. Again, exam packs will be linked into the description. Feel free to share. Okay, share, like, and subscribe, as I say. Share the exam packs on it, not share my website, YouTube site. You can do. All right, okay, so let's move on. I think we've almost got to the end of it. So we've done this in good time, 1 hour and 11 so far on my clock. So figure 3 shows a path of toy car along a section of the racetrack. So at A, what do you know at A? You're moving with kinetic energy. What do you know at B? You're moving still, and you've now got potential energy as well, gravitational potential energy. And by the time you got to C, you've now got kinetic energy. Believe it or not, I think I've just answered the question just by annotating what I know. What do I know about the kinetic energy at A? So this is the obvious stuff, because they said ignore that. That means EK at A is equal to EK plus EP at B, which is equal to EK at C, conservation of energy, because we're ignoring air resistance. And I think I've just answered the question even though I'm ready. Car moves along the track from position A to B, then to C. Describe how energy stores of the car changes as the car moves along the track from position A to C. So what do we know? In fact, if I wrote this down, I'd have got most of the marks, I think. So let's just write it here. So EK at A is equal to EK plus EP at B, which is equal to EK at C. Okay, so what happens when you go from A to B, because we need a bit of detail, some of the kinetic energy of the car, EK, decreases. It's still moving, because otherwise you wouldn't complete the loop, and EP, potential energy, increases. Okay, so the loss in EK equals the gain in EP. Okay, and then let's do B to C. So what's happened B to C? The GPE, or EP, sorry, I've lost my form, decreases, and EK, kinetic energy, increases. And again, we could do the same. So the loss in EP, potential energy, is equal to the gain in EK. Okay, so again, like I said, just by annotating, I've actually answered the question. Okay, so let me rub that off. Doesn't make sense if you look at it later. Right, so, and again, I'm expecting this as a mathematical question next year. Okay, but they love these combining these conservation of energy. Okay, so last part of the paper. So at the end of the racetrack, the toy car passes through a light gate that measures the speed of the car. So let's ask, so which two measurements are needed to determine the speed of the car? So what do you know? Speed is distance over time. Okay, so you need a distance, you need a time. So time for the car to pass the light gate, total length of the track or length of the car. So what you need to be able to know is, what does a light gate look like? So a light gate is basically, it looks something like this, probably attached to a clamp, and there's usually two of them. Now, if you haven't seen one, don't worry. They're really fiddly to set up, and no teacher wants to set up. It takes longer to set up than to actually use. And what would happen? The car would essentially go through. So when it goes through the first light gate, the light gate will trip. The timer will start when the front of the car goes through, and then it'll stop recording when the back of the car goes through. So we'll work out a velocity there maybe, and then as it travels through the next one, it'll work out a final velocity there. So we'll work out two velocities for you, and then you could work out an acceleration. And like I said, these will be connected to a data logger or a computer, an old-fashioned computer, or just a laptop or whatever, or some sort of something to be able to visualize or collect the data for you. So you don't need the length of the whole racetrack. You want to work out the speed of the car in any one of them. You need to know the length of the car that's going through and the time that the light gate was triggered. If you've got two light gates, you could just simply work out the acceleration. Okay, so what do we need here? We need the length of the toy car. Okay, so that's it really. That's the whole of the paper. We've done that quite quickly, and I've done that by talking to you as well. Hopefully you can see my thoughts, my thinking, my reasoning when I go through these, and that's what you're going to be able to do. So if you think you can't do it in an hour and 45, we've done it in less. Okay, and I've waffled on for quite a lot. Okay, and I've wrote in my best handwriting, so I took my time. Actually, it's not possible. Right, let's move on. So here's my predictions then. So this is what's happened in terms of required practicals. So they always test about 2 required practicals a paper. Could be up to 20, 25 marks in total, which is a quarter of the paper, isn't it? So look here. I don't think specific heat capacity is coming because they've tested it to death. Okay. What could potentially be coming is this. RP2, thermal insulation, the different layers of the same insulation or same thickness of insulation but different types of insulation, and measuring how the temperature of something cools or cools down, rate of cooling, cooling graphs and so on. That hasn't come up for 3 years now. Okay, so I'm expecting that to come up in some form. Whether it comes up as a 6 marker, I highly doubt it. It's a very hard plan to write, and it's not a long plan because you're not really, it doesn't take long to set up and there's not much to think about. So I'm not expecting that as a 6 marker. Resistance against length, there could be potentially something here in terms of graphs, maybe, okay, or analysis or calculation, not necessarily the method because they've sort of did that, but they could do, like I said. And I'm not putting my haste on it because it's not the most interesting 6 marker. Maybe that one. Okay. IV graphs, I think they've done it to death now. They've covered all aspects of an IV graph. But like I said, don't take my word for it. Obviously, you're still going to plan for all 5 RP5s. But I would certainly spend more time on these for the time being. And what I've done in the description, I've sent you a link to a Google Drive where I've collated RP2, RP3, RP5 questions for you. Okay, so of course, download them, share them, no problems with that. Practice, practice, practice. Watch YouTube videos. There's lots of really good school websites of other schools, of other people, sorry, who go through the practical and so on. Just be careful. They don't necessarily do it the same way as we've done it or you've done it in class because of the practical apparatus available. So that's what I'm expecting in terms of required practicals. Okay, obviously I've talked about what sort of questions are going to come up, what sort of topics. Okay, so even if you're playing this video in double speed, just pay attention to what's going on. So let's move on to the other thing I'm trying to predict is the sort of questions, so sort of calculations you're going to use. Now, if you look every year, there's always been some sort of conservation of energy. So that's the one we did this year, conservation of energy last year, and this one, E equals half KE squared. So this year, or 2025 paper, there was elastic into kinetic. 2024, there was elastic into GPE. 2023, there was elastic into, I think that's meant to be potential energy. Oh no, there wasn't one there. Okay, that's interesting. So it wasn't a conversion question there. So if that is going to be a conversion question, I think it's going to be GPE to KE. Or if it was GPE to elastic energy, or elastic energy to GPE, or elastic energy to half mv squared, you've got loads of questions. And again, I've made a pack of this, so expect that. You're always going to get an E equals mc delta theta. Can you see? It's probably the most pertinent thing about chapter 2. Where I'm expecting an E equals mc delta theta, if they're going to be really tricky, equal to an ml. Okay, or even a total energy. If something is heated up and melted, so I'm expecting a total energy is mc delta theta plus ml. Okay, and the last time they did a question like that was in about 2018, I think. And again, I've put some questions for you to look at, so make sure you have a go at them. If you don't, choice is yours on that first. I'm not going to lose any sleep over it, but it's your preparation, isn't it? Energy resources, there's always questions about energy resources. There hasn't been a question about the national grid for a while. So remember the national grid, so you've got the 2 pylons. Okay, and what do? They send it a high voltage. Why do they send a high voltage? Because that means it's low current, less heating effect. So therefore it's efficient. So that was, no, that's not a calculation. That's just a description. I don't know why I put it there. It's just the only thing that stood out to me. Electric circuits expect everything. V equals IR, Q equals IT. That's pretty much it. Electricity in the home, E equals QV, P equals I squared R. Because P equals I squared R is only a higher tier formula, expect to use it. Molecules and matter, now this is the one. They have not used PV equals a constant for a while. So if you look, it's not come up. Oh, now what is that to you? That's P1V1 equals P2V2. So it sort of stuck out to me that they're not used this at all. That here just means they asked for a pressure description. In fact, they asked that in 2025 anyway. So E equals ML is going to come up, of course. I'm expecting E equals ML to come up with E equals MC delta theta. That'll be a lovely 6 marker. Okay, everything, lots of 2 formulas combined, some conversions of masses, etc., etc. So expect that. Every year, you're going to expect half-life calculations, although there wasn't one in 2024, but do expect it. They talked about fusion in 2025, but they talked about fission. Okay, but I expect they haven't talked about nuclear reactor and chain reactions, so I'm expecting that also. Okay, so that's just my take on it. Obviously, take advice from me or take advice from someone else. I'm not really too worried about that, but just make sure your preparation is thorough. Okay, so again, good luck with your tests, and hope paper 2 walkthrough coming soon.